Standing on the existing protocols, I welcome you all to today's lecture. As we all know that this lecture is a simple and ICTP research in pairs lectures on theory on partial differential equation. So today, which is going to be our last day, as I said yesterday, we are going to be looking at the characteristics mapping method for incompressible Euler equation. Incompressible Euler equation. And I said, as I said earlier yesterday, that the characteristics method, the characteristics mapping method is actually an advancement on the Chaptis method that we have seen earlier in this course, that is in the first D. So today we are going to see how to actually apply it to solve the incompressible Euler equation. The characteristics mapping method is a method for solving linear advection problems with arbitrary initial conditions. Its unique property is the decoupling of the computational and solution representation grids, thus allowing small length scales to be accurately represented in the solution with overall low computational cost. This method was actually developed by the group of Professor Kai Schneider of International Mathematics, the Marcel, in Aix-Marseille University here in France. And they have been able to come up with a computer program which is designed in CUDA and C++. It is already domiciled in Git. You can just browse the CMM method. You browse the CMM method, that is characteristics mapping method, CMM. CMM. You can just browse this, you see it. The codes are domiciled in GitHub. You can see them there, and then they also have the MATLAB equivalent of the code for solving these problems. You can just go in there and then you find the code there, and all the detailed explanation on how to run the code are clearly stated in the code. So let's move forward. Then the linear advection equation. Advection is the process of transport of quantities in a velocity field. That is, when we talk of the advection, then two things are involved. One, the quantity that will be advected, and then again, the fluid in which the quantity is going to be advected. So the quantity could be properties of fluid, such as mass, that is, it can be a mass that we just want to transport, or the momentum, or generally microscopic quantity like the track density. The velocity field could be a constant or a function of space and time. So the velocity of the fluid for the quantity that will be advected could either be constant or depend on a space variable. The following partial differential equation describe the phenomenon. So this equation what we have here in 2.1 here describe the advected, the linear advection equation. We can see here this is the phi t, and then this is u, which is the velocity of the quantity that will be advected, and then we have phi of t here, which is equal to 0. Where x, these are the variables, the independent variables, which are in this, and then we have the time. Then we have this function into this to the real number is the scalar, which is the scalar field representing a quantity, and u here, as we say, is the velocity of the quantity to be advected in one dimension with constant velocity. The equation simplifies to the following. Yeah, supposing it is just in one dimension, that is just along a single dimension, then this equation will simplify to what we have here in equation 2.2. Then the equation is called nonlinear when the velocity field also depends on the scalar field v. Yeah, of course, we know what we discussed earlier regarding quasi-linear and non-linear first order PDE, which makes the theory more involved and discussed later. So we can see here, this is the graph showing the advection in constant velocity. Supposing what we are advecting a quantity, maybe let's say mass, in a constant velocity. This is the graph of the velocity. We can see the fashion. And then here now, if the velocity is not constant, supposing it depends on some space variable, let's say x, we can see the graph we can see this is emerging from the same point, but they move, there is a kind of a little drag here in the movement due to the fact that the quantity, the velocity is not constant. But here you can see that it moves in what? In a regular fashion. For when t is equal to 0, t is equal to 1, t is equal to 2. The same thing here for t equals to 0, t equals to 1, 2 equals to 2. We can see that there is a kind of a slow down in the movement of this, and all of them are originating from the same place. So these are figure 2.1 advection of scalar quantity. Then the scope of this work spans the Cauchy problem of advection equation. Yes, we are going to be looking at the Cauchy problem generally to see how we can actually use the CMM to solve a problem in this form. Then later develop to fluid flow problems. This is it now. Now it becomes a fluid flow problem because now a condition has been attached. You can see phi of x, 0 is equal to g of x now, which is the initial phi of x naught. You can see at t equals to 0 here. This is what we have here. So, of course, we use this, and then g is also a function, given function representing the velocity field and the initial condition respectively. So this is the initial condition. We are also given that g is continuously differentiable. That is, g here, the function here is continuously differentiable. That means it is continuous within the given region. Then the problem is of central importance in the area of computational fluid dynamics, for it provides a minimal model for analysis of numerical methods aiming to solve complex fluid flow problems. The advection quantity is hyperbolic in nature, yeah, clearly we know that, and has a finite propagation speed. So the solution at each point travels along globally well-defined curves, which are called the characteristics curve. Now, we recollect when we talk about the characteristics method, which is also known as the Chapty method. This is where it actually has an overlap with the characteristics method here, because here as we say that what the solution at each point travels along a globally well-defined curves, which are called the characteristics curve. So the method of characteristics proposes for the Cauchy problem, for the non-homogeneous advection problem of this form. Here now look at the problem here of this is non-homogeneous because the f of x here is what? Is not equal to 0. So this equation here is non-homogeneous. So this is like the non-homogeneous look like. Then the solution is given as what we have here to be equal to this file of what is it called, gamma of s, comma t, to be equal to g of gamma of 0 here plus the integral from 0 to t of what we have in here. Here, this was actually obtained generally, if we recall, from the Picard's rule, where we have, supposing we have a first order differential equation. But here now, we are going to be looking at the PDE rather than just the first order differential equation. So this is what we have. So this is what we have here. This is what we have here to obtain this phi. But then this arc that appear here, this is what we use to also obtain. By the time we obtain the value for this, from here you can see this is where the velocity comes in. So we are going to make use of this to obtain this. And once we are able to get this, then we can then plug it into this equation for us to obtain the approximation for this. And this is how this will continue until we are able to obtain the final solution where we are going to. Of course, f is a function in here and is known as the source term. Then the solution simplifies to the homogeneous equation if f of x, t is equal to 0. And if f of x, t is equal to 0, surely, let's come back to this place. We will see that if it is 0, then of course this term will not be there again because this is now 0. So you can see this is what the equation will reduce to. But then this will still remain this, so that immediately we obtain this value for each grid point. Once we obtain this value, we substitute it in here for us to obtain, we substitute it in here for us to obtain the solution at that particular point for this. Then the solution at any point in space and time depends only on the point. More precisely, it remains constant in time along the locus dictated by the following initial value problems. So let us look at this, the other figure, figure 4.2, show the characteristic curve, the solution to the initial value problem for advection of scalar quantity phi with a velocity u of x. We can see it here. This is the representation of the characteristic curve. Now let's look at it very well. We will see that this is, of course, when t is equal to 0, t is equal to 1, and then t is equal to 2. Now these are the curves. Now let's look at them very well. We can see these are this for this. You can see it. You can see how it moves. You can see this. We can also see this, and then again, then we can then look. This is for file. The blue here is for file, and then we can see how the graph moves. You can see it. You can see so it's higher than this. We can see where it's meet up with all this. You can see all that. So the representation of characteristic for one-dimensional advection problem. This is also how it is, and then you can see this is the domain from 0 to what? To 2 pi, which means x takes from 0 to 2 pi, and then t here is just from 0 to 2. That is the time. So since the solution of the Cauchy problem in equation 2.3, the solution in equation 3.3 can be written in this form, having a unique point xf for xg, the characteristics mapping method proposed to compute a map x such that x goes into this, and then we have our file of g to be equal, file of x comma t to be equal to g of this. So from the global existence and uniqueness of characteristic curve initial value problem given in equation 2.9, our style here is guaranteed to be a bijective map. That is, this style here is going to be both injective and subjective. This is what we call this style here is what we call the flow map. That's what we call the flow map. Then the characteristics map can be computed by solving this given equation here in equation 2.5. Clearly here we can see this is the initial condition here as given here as bar. So x bar here, you can see it, we can see this, you can see what we have here. So the above Cauchy problem is solved using the GALS. GALS is actually, the CMM is an improvement on this GALS method. But we are looking at CLS, so that CMM, that is why we will not bother ourselves on this GALS method. But CMM is an improvement on GALS method. So transforming the problem into this form removes the smoothment condition from the initial condition G. Then this allows us to solve the advection problem with arbitrary initial condition. Moreover, the analysis of the error of approximation show a reduction for general case. So we can see this. This is how it moves. You see, when t is equal to 0, we can see the grids. You can see how they are. Then when t is equal to 0.1, immediately t increases now. You can see that there is a movement. You see, there is a movement. You can see along the grids there is a movement. By the time you increase it again, what happened? The movement increases. You can see there is a kind of a distortion. You see, by the time you increase it again, this is how it will look. And as you continue to increase it, the grids will continue to move, and then the whole system will be distorted. So advection of 2D map in velocity field in equation 2.16. So that's what we have here. Then figure 2.7 show the evolution of the characteristics map in the two-dimensional velocity field prescribed in the equation 2.16. So here now, if we are talking of our two dimension, you can see, so this is a velocity, this is another velocity, let's say along y, u is a velocity along x, and this v here is a velocity along y. So remapping. According to the definition of characteristic map, they can be composed to form another map. Yes, if we look at the flow map, by the time we take the composite function of two flow maps, we are going to get another flow map. So that is why you see that we have this here. You can see 2.17. So the composition of two cubic maps gives a sixth other polynomial in each variables, forming another cubic map from it. Is a projection which can be computed on a final grid, thus retaining more subgrid features. So this makes the method more robust because every time the global error of approximation grows, the map can be resampled on a final grid. That is, what we are trying to say is that this actually, it can adapt. Yes, the method has the ability to adapt. So once the system realizes that it's choosing a particular grid, the solution will be, it's going to take more time to obtain the solution, then this method has that ability to adapt with another grid that will give us a solution at a lower time. So these allow us to represent the solution on a final grid than the grid on which the computation of this is performed. So we can move to another grid. It has that adaptation. So we can see this. Let's look at this. Sorry. You can see this. Look at what we have here. This is before this is before the movement. This one is before the movement. We can see what we have here. Then we can see this. This is the flow map. This is the flow map. And then by the time there is a movement here, then the whole of this is being distorted to have something like this. You can see that. We can see that there is a movement in this. Then let us look at the 2D incompressible Euler equation. Euler equation are a set of nonlinear hyperbolic conservation laws governing the flow of adiabatic and inviscid flow, along with the incompressibility constraint. It is a very reasonable model for low mass number flow. Euler equation provides an excellent case for testing the characteristic mapping method on nonlinear fluid flow problems. Applying the incompressibility constraint, the equation simplifies to the following, which is what we have here. So we want to look at the Euler equation. We can see it here. We can see what we have here. We can see here. This is the velocity, this is the density, and this is the pressure. So here now, where U is the velocity, P is the density, of course, P is the pressure. So the incompressibility condition implies that the volume span by a certain fluid element remains constant in time. Now, supposing now we now introduce the vorticity by taking the call of the velocity, that will give us what we have here. So the equation can be written in the form of a non-homogeneous, non-linear transport equation called the vorticity transport equation, which is obtained by taking the call of that equation. By the time we take the call of that equation, this is what we are going to obtain. What we have here in equation 4.2. Further, assuming the flow to be two-dimensional, yes, and paratropic, which implies that the gradient of P cross P is equal to 0. So the equation simplifies to homogeneous transport equation. By the time this time here reduced to 0, then this equation will reduce to what? To a homogeneous transport equation. So we can see that is why we have this. This is what it's going to reduce to. So the equation is solved together with the incompressibility constraint. This is the incompressibility constraint. This is it. Along with initial data of U given and in periodic boundary condition. So now let us look at how do we now use the characteristics mapping to actually solve the Euler equation. This. Now let us look at the algorithm. Characteristic mapping method for Euler equation. While solving the equation, we need a relation to compute advecting velocity field such that the incompressibility constraint is satisfied. The following constructions allow that. Yes, these are the constructions. Sorry, these are the constructions. We can see that if this is the stream function here, we can see, and then this one is what we call the perpendicular distance. So by the time we take the perpendicular distance of the what is it called, of the vorticity, we are going to obtain the stream function. Okay, so here now, sorry. So now, sorry, this is the perpendicular distance. Sorry. This is the perpendicular distance. This is the perpendicular distance. So by the time we take and the interpretation of the perpendicular distance implies this, that is di y, comma, minus di x. That is this vector here. That is how we obtain the perpendicular distance. So algorithm 4 shows the basic overview of the step of the characteristics mapping method. The problem is initialized with an initial Cauchy data omega naught defined on a set of points xg, forming a uniform grid with grid spacing h and periodic boundary conditions. So a characteristic map of this set to identity, that is x, side of x comma 0 equals to x, is taken as the initial condition for the map. So this is what we assume to be the initial condition, an identity map. So a time step dt is chosen such that constraint in equation 2.12 is followed throughout the desired running time of the simulation, and time tn is defined to be n dot dt. So this is the algorithm. This is the algorithm. You can see this is the initial condition here, which is the identity map that we discussed. And then this is the vorticity, the initial condition, the initial vorticity. Then we choose we choose our n here to be equal to 0, and then t naught, that is the initial time, is taken to be 0. And then this is the number of time the system is going to run, and then we have dt here. So while this n is less than this number of time, then we say that what the computer should carry out this set of instruction. That is, this is the vorticity, should carry out this. Already we know what this is because this one is given from here. So this should be computed from here and dump in here. Then you should then advect that quantity again to obtain this. Then add 1 to n. So this will continue until when this is equal to this. Once this is equal to this, it will stop. Then it will now return this particular statement as the as our vorticity. That is the omega of n of x. So this is just the brief of the algorithm behind the characteristic mapping for solving incompressible Euler equation. Yeah, this is actually heavy because it requires a lot of computer codes to actually execute this particular algorithm we are seeing. But Professor Kai, the team of Professor Kai here in IX Marcel, has already helped us to develop both the MATLAB code and the C++ and the CUDA code in order to make use of these innovative method, which is known as a characteristics method for solving incompressible Euler equation. So now, having said all this, then we can then look at, let us now look at just before I move, these are some of those very few references for characteristic mapping method. Students of knowledge can just visit this particular work. Then you find a more detail of the method. And then again, what is it called that we use, the slide, and then the note that we put together, the note that we use for this course was put together by Professor Yomi Monde Ayesimi and I myself, Abdulhakeem Yusuf. That note can be obtained from the Federal University of Technology Mina repository. On clicking this link, students of knowledge can always get that material. And then again, students are advised to go further into so many other textbooks on PDE in order to have a better knowledge of what we have discussed in this course. So far, in this course, what we have done so far is, as we have said, this course actually started on the 27th. Sorry, this is May, please. 27th of May, please. This is it's a mistake. 27th of May, 2024 to today, which is 30th. So before I give the recap on this course, I would like to thank SIMPA and ICTP for giving me this rare opportunity to be here today in Marseille, France, here in CIRM here, to deliver this lecture. I really appreciate this great organization for this wonderful opportunity given to me to be here on this research. And then again, I would also like to thank my my host in person of Professor Kai Schneider. Yeah, I call him the problem solver. As long as the problem has to do with mathematics, once you meet him, I bet you if your problem is not solved 100%, it will be at least 50% resolved. Yes, I really appreciate him for giving me the opportunity to visit him in order to carry out a research work in the area of the vortex merger, which is still ongoing actually. So, as we have said, this course is the theory of partial differential equation, and on doing that, these are the things we try to look at. We give or we divide the course into 4 different parts. We have section 1 where we discuss the first order partial differential equation, section 2 partial differential equation of second and higher orders, and section 3 second order differential equation 2, and then section 4 we have boundary value problems. And then in the first section here we look at what we understand by a partial differential equation generally, which we give an overview here. And then again, we then move further to talk about the general form of the two independent variable here, which is x and y here, in order to talk about the general form or the general form of first order PDE in 2 variables x and y, with u here as the unknown function and u x, u y here as the first order partial derivative of u with respect to x and y. Then we then talk about the types of first order PDE. We discuss the linear first order PDE, the quasi-linear first order PDE, and then we also talk about the non-linear first order PDE. Our discussion on this, we said a lot on how we can actually identify when a PDE is linear, when it is quasi-linear, and when it is non-linear, where we talk about what? The coefficient of the derivatives that appear. What is their condition? If we look at it, this one is just a normal, that's a of x, y, b of x, y, c of x, y, d of x, y are just given functions. So if you look at it, they are just given functions, so which makes this equation to be a linear. And then here again, if you look at these for quasi-linear, we'll see that the coefficient of the derivative depends also on the independent variable, whereas this one here don't depend on the unknown function, unknown functions u. But these ones here depends. You can see that a of u, b of u depends on the unknown function also, which is u. So this is what makes it to be quasi-linear first order PDE. And then we talk about the non-linear PDE, which is what we have here in 1.1.3. And then we then move on to talk about the derivation of partial differential equation. How can we obtain our partial differential equation from a given function? So we talk about that once we have, supposing we have a family of surfaces, which is given here in 1.1.4, we say that what the 2 constants that appear here should be what? Should be eliminated. And how do we eliminate constant from here? We are going to differentiate the function given with respect to x and then with respect to y. So, and on doing that, we said we are going to obtain these equation here, 1.1.5 and 1.1.6, by the time you differentiate with respect to x and then with respect to y. So then here is also the derivation, and then derivation. Then consider the family of surfaces here, which is given as a file of f, g equal to 0. Then on differentiating these two, this arrives into these differential equations, where we took our du x to be equal to p and du y to be equal to q. So that's reduced the equation to what we have in equation 1.1.9, which is in this form. And then again, we see that by the time we want to try to eliminate diphi dig and diphi dif, we are going to treat this equation in form of what? A system of equation. Then we decided that day we wrote it out in form of the matrix form, and we say that if the whole lot, if this is equal to 0, this is also equal to 0, it's just appropriate to say that what? The what's it called? The determinant of the coefficient of di-phi di-g and di-phi di-f is equal to 0. And by the time we take the determinant of this, that will just simply give us what we have here, with this p here equal to this, q equal to this, and r equal to this. And we see that this particular p here means di-f di-y, di-g di-u, minus di-f di-u, di-g di-y. Same thing goes with this, same thing goes with this. And that was how we move on. Then we give an example on how to obtain a differential equation from this given equation here. And we say the first thing we are going to do is to eliminate the two constants here. And what are the two constants that appear here? We have them a and b. So we differentiate this with respect to x, we differentiate it also with respect to y. And on doing that, we're able to obtain this, and then we then substitute back into the original equation, and that gives us what we have here in equation 5. So then we now look at the solution of Lagrange's linear equation. The general particular differential equation, this where p, q, and r are functions of x and y, is referred to as the Lagrange's linear equation, which is the equation we have here. This is the general form of the Lagrange's equation. Then we now look at the derivation. We can see we talk about all these, and then we were able to arrive here. Since 1.1.15 here determines the integral curve of 1.1.6, then we have this. Now, considering any functional relationship when f is differentiable, then we have this particular equation here. So eliminating again the f and the f di-g, that equation reduced to what we have in equation 1.1.20. Then we now say that consider any two solutions, omega which is equal to c. Then differentiating partially, we have the following. By the time we differentiate this omega, which is a function of x, y, and the unknown function u, that will give us what we have in here. And then we can move on. Then we say that for this particular equation here to be satisfied, then of course, then p will have to take this value, and q will have to also take this value. We substitute them back into that equation, and we saw that it was equal to 0. So in view of that, we're able to arrive at what we have here in 1.1.25. Then we say that our Jacobian is this. Then since the partial derivative of f and g and w are supposedly continuous, then the vanish of the Jacobian j in this implies a functional relation of the form omega equal to phi of f comma g. Hence, this minus this will give us this, and then we have this. And this was how we ended the proof. Then we now talk about the general method for solving the first order partial differential equations. And we talk about two methods, the Chaptis method and then the Jacobi's method. We talk about them. So, and then we say that for the Chaptis method, we say that given this particular PDE, then since u is a function of both x and y, then we thus have that du surely will give us what we have in here. So if we have another function which is given as this, then it will be possible to evaluate p and q from the two given functions, this and this, in form of p equal to phi and q is equal to this capital phi of x comma y comma u, which is equal to a. So we move on, and then obtain this, then yeah, and then I think okay, sorry, and after everything, we're able to give the general form. We're able to arrive at we say this is a linear differential equation of order 1 that must be satisfied. Its integrals are integrals of the Lagrange's auxiliary equation. So this equation 1.2.15 are known as Chaptis auxiliary equation, which is also known as the characteristics method. So any integral of this involving p or q, both is taken for the required second relation. In fact, the simplest relation of this is taken as 1.2.3, and then obtaining 1.2.3, p and q are determined from 1.2.1 to 1.2.3, and the value substituted into 1.2.2, which on integration will obtain the required complete solution of the given differential equation. Then we now move on again to talk about the Jacobi's method, and then the first thing we did here was to consider this theorem that said that if the function phi1 of x1, x2, x3 poses continuous partial first derivative in this, then we say that phi1, phi2, phi2 of this is an exact differential equation if and only if these three conditions are satisfied. So then we move on, say a lot about this Chapters equation. Then determination of this function g2 and g3. Here also differentiating the g2 in terms of x1, in terms of x2, in terms of x3, like that. And then g3 also gives us, because we recall that this g2 and g3 depends on x, y, p1, p2, x, y, p1, p2, p3. So for us to carry out that derivative, of course, the partial derivative is going to be this long like this. So that is how we obtain all this. Then we then move on to eliminate the p1, the x1, the p2, the x2, the p3, the x3. And the equation reduced to what we have here in 1.2.33. And then we have this. Then here now we then expand this and we say that we need to take note of this particular identity, that the g2, g3 of the xa, pj is the same thing as minus, that is the opposite of one another, these two. So here now, this is what we have. And then here we then took, we assume, we took our L to be equal to, that is, we put the two of them together. And then we get, we obtain our L to be equal to what we have here, M here, N here. And then G2, G3 is what we have in here. So this equation now, on reducing this, you can see it. We have this L, M, N, and everything here is equal to minus G2, G3. Then similar computation happen here. Then we have this. So, and then we're able to obtain at the end of the day the Jacobi's auxiliary differential equation, which is given here in 1.2.40. Then furthermore, on Jacobian's method, then we'll now look at some special cases for this Jacobian. We're able to identify this identity, and then that was how we ended our section 1. Then moving to section 2, we talk about the partial differential equation of second and higher orders. And then we say that what the linear equation, the most general linear mth order partial differential equation, is often in this form 2.1, where we say that all these A, B, C, M, and all these are what? They are constant or functions of x and y. So we reduce it into this, then we have what we have in here. Then later we'll now say that, okay, what happened? Then we'll now further reduce the whole general equation by taking our di x to be p and di prime to be di y, so that the equation will reduce, and that was how we were able to obtain what we have here in 2.4. Mind you, this dm here means di to the power of m di x m. Then d prime here just means di y. So that is how we obtain this. And then this f of x, y here is signifying the inhomogeneous part of the differential equation, in which then f of d, prime is a differential operator of order m. Then the corresponding homogeneous differential equation reduced to 2.4, given by this. That is, for homogeneous, this f of x, y will now be equal to 0. Then definition 2.1, the differential operator is said to be irreducible if it can be decomposed into factors of this form. If we can reduce any given differential equation into this form, in which alpha and beta and gamma here are all constant, then we say that what? It is reducible. But if not, it is irreducible. So method of solution. The solution of 2.4 is analogous to that of an m-order ordinary differential equation, which comprises of a complementary function that contains m arbitrary constant and a particular integral pi that contains no arbitrary constant. So in this case, the complementary function is the solution of 2.5. That is, by the time you solve the homogeneous part of the differential equation, you obtain the complementary function. Then you now solve the inhomogeneous part of the differential equation so that we can obtain the particular integral. Then now let us now look at the complementary function. In order to obtain the complementary function of the corresponding solution 2.5, we recall this theorem from the elementary calculus, which stated that if differential operator f of d, prime, then the general solution of 2.5, that is f of this, is equal to alpha d plus beta d prime plus gamma, everything to the power of m, multiplied by, and then we have what is equal the dependent function here, and everything here is equal to 0, where m is the positive integer, giving us u equal to this in equation 2.7. Then for this, we then move forward to prove this theorem. Yes, we're able to show this proof using mathematical induction. We're able to show the proving using math induction. So that's what we have in here. Then can move. Then for particular integral, we now see that for particular integral, this is what we are going to assume. We are going to assume the product of all these. For particular integral, we are going to assume the product of all these. And there are two ways to it. This is the first one. We start the implementation of the inversion operation from the last factor on the right as what we have here. So we equate the whole of this to be equal to g of x. This is just an arbitrary function, this g of x comma y. So by the time we now, I think we cross multiply so that we can have this. Then you can see this is what we have. And this is a first order differential equation. Then this is the Lagrange's linear equation with corresponding auxiliary equation. So this is the auxiliary equation for this equation that we have here. So we can see that then now we can now take this pair dx d alpha to be equal to dy d beta, and that will give us what we have in here to be equal to 0. Then by the time we integrate this, we obtain this. You know, when we integrate 0, we are going to have c. So we can have this. Then the next thing we are now going to do is to take the pair of this with dx, and that will give us this, and then we're able to resolve the differential equation into what we have in here. And we say that alpha m must not be equal to 0, so that this equation will be defined. This must not be equal to 0. So now that we now have this kind of, you can see we have a differential equation now in what? In G. So we now introduce the method of our integrating factor to what? To obtain the solution to this differential equation. And on doing that, we say that the differential equation g of x will give us this. Though we have not carried out the integral, this is what we are going to have. Then again, of course, we are expected to go back and take the pair of this dig with dy divided by what? Beta m. The same process go in there, and we are going. This is what we are going to obtain as the solution for that. So we observe that no arbitrary constant, as we have said earlier, that for particular integral, there will be no arbitrary constant. So this way we operate from the remaining factor from right to the first on the left in turn to finally obtain the pi. Then for the method 2, we say that for the method 2, what we need to do for the method 2 is to carry out what we call what? The we carry out what we call partial fraction. So here we assume each and every one of them to be a divisor of what? Of a constant. Then we resolve it. Then we then pick them one after the other. Although by the time we pick one and solve it, we'll be able to generate the solution for others. So this is how we move by picking the first one, and then we obtain the solution for when we have it for just alpha 1. And then at the end of the day, this is what we have for when we pick the pair of the function of g with x, and then this one is what we have when we pick it with respect to y. So sorry, there is a typographical error here. This one should be dy, not dx. So then we now talk about some special cases. We recall that the particular integral of 2.6 is giving us up equals to 1 all over the differential equation multiplied by f of x. So this is determined almost the same way as that of ODE. So the inverse operator may be extended using the binomial theorem, and thereafter performing the integration of these d inverse with respect to x and y respectively. Then the I corresponding to certain special functions may be obtained by much shorter method than the general method. So in this section, we note the following pertinent rules. 1, we say that what if we have this, this is what we are going to have, provided this is not equal to 0. This is for case 1. Then let's look at what we have for case 2. Now, supposing there is another function multiplying this, then we say that everything here should be taken as this. Then we are now going to introduce what? A and B into this. So that will now give us what we have in here, then multiply by this 5. where this file is just an arbitrary function. So if a and b is equal to 0 in case 1, then pi is obtained as follows. Then case 4, we say that, okay, now if we now have a trig function, cos of alpha x plus ax plus by, then we resolve it into what we have in here. We can see that is just like a quadratic function. So this is what we have here. And then if this is equal to 0, this case will fail because this will be undefined. So we then compute the pi by considering the real and the imaginary part. That means we're now going to split it into real and imaginary parts by introducing what? These complex function here. Then at the end of the day, we are going to have the solution in terms of real and imaginary. So we are going to pick the real part or the imaginary part as the case may be. And then we have the fifth case. I think that is the last case. And in this case, we apply the polynomial theorem to the inverse operator and then operate on xm, ym. So that is how we ended that function. Then we now, section. Then we now move on to section 3. And here in section 3, we discuss, we talk about partial differential equation of the Cauchy-Euler type. Equation of the Cauchy-Euler type are PDEs of this form. Here, we talk about transformation a lot. Here, you can see that the coefficient of the derivative here is x. The coefficient of this is what? Is y. Once we have this kind of differential equation, then we'll have to introduce some of these transforms that we have in here. You can see, we say s here should be taken as ln x, t as ln y, this theta has dds, and then we have phi here as what? As di t. So we move on. This is what we have. Then the first thing we did, I think, okay, we gave for this to be equal to this. This will give us this. And we say this will give us this. And we say that if this one is x to the power of 4, d to the power of 4, this will be what? Theta in the bracket of theta minus 1, theta minus 2, theta minus 3, then multiply by what? Multiply by u. So the same thing happened to this. If it is to the power of 4, that is how we are going to resolve it. So then example, then transforming the following PDE to linear form. So what do we do now? Supposing we have these PDE now. So we are now going to introduce all these transformations that we have in this 3.3. We substitute them into this differential equation. And on doing that, you can see that after all this substitution, the differential equation, as complex as it looks, it reduced to this simple differential equation here, which we can just separate and obtain our what? Our solution. And another example here now, also we can see this. And what we did here was what? To also introduce all these identity in order to what? To reduce these differential equation and at the same time linearize it. And introducing all those, what is it called that we have in here? Di u di x is the same thing as di u di s does di s di x, which is equal to what? X di u di s. The same thing with this, or we say that what di u di s is equal to 1 upon x di u di x. So that means we can take, if di u di s is equal to 1 upon x di u di x, of course, by the time we take the derivative of this one, these words for the second time, then we should be able to say that 1 upon x squared di squared u di x squared is the same thing as di squared u di s squared. So that is how we're able to resolve all these. We can see that. Then the next thing is we also transform the other part, which is this. Then by the time we substitute them into that differential equation, it reduces to what we have here, which is just like a difference of which is just difference of 2 squared. And once we're able to look at it here, difference of 2 squared equal to 0, we can easily carry out this integral. Then we talk about second order PDE with variable coefficient. So supposing now those PDE now has what we call the variable coefficient, then we then talk about all these transformations that we have in here that we are going to make use of in order to reduce those differential equations. Although first of all, we say that what a partial differential equation with variable coefficient is that which contains at least one of the partial derivative of the second order and none higher than the second. This is simplified if we consider the case of two independent variables. So now we have this. Then now let us now look at the example that we solved that day. We say that solve s is equal to 2x plus 2y. So we just introduce s from what we have here. And we say that, so here now, we say that S is what? Is die squared U, die X, die Y. So we have it here. And for us to obtain this solution, we integrate this with respect to X, then we integrate with respect to Y. We integrate with respect to Y, we are going to add what? A function of X. Then again, we then integrate with respect to what? To X. Then we now add a function of what? A function of Y. So that is why we obtain this. There are no conditions attached to the problem. That is why we are not able to obtain the exact function. So we just leave them as arbitrary function. So the same thing here with note, we say that we know that 3.5 is a second order quasi-linear PDE, and then it is linear if it can be put in this form, in which R, S, T, P, and U and V are functions of X and Y. So we also look at this differential equations. Then now we now talk about the Monge's method also. Then we look at the transforms that are involved in this method, which happens to be these also. Then we have all these. You can still remember all these. Then the general form of second order with variable coefficient admitting a first order integral and its solution. So we talk about all these also. All these are all about transformation. We introduce all those transforms to solve the differential equation. And then we say that in implementing this procedure, we note these three key points here, which we explained earlier. Then we then move on to our section 4, which happens to be the last section. And in this section, we started with boundary value problems. And then we said, what are boundary value problems? We say that what? These are differential equations here, or partial differential equations here, that have conditions attached to them. And these conditions are given at what? Some particular boundaries. So we say that what? If a second order differential equation 4.1 is to be solved within a specified region of space in which the value of the dependent variables u are specified at the boundary they are, then the resulting problem is referred to as a boundary value problem. That is, when we have a differential equation, it is not a problem until we add a condition. Once a condition is attached to it, then it becomes a problem. Then it's either it is an initial value problem or a boundary value problem. This depends on the kind of condition that is attached to the differential equation. These boundaries need not to enclose a finite volume. In this case, one of the boundaries may be at infinity. Yes, the boundary may be at infinity. So then we say that what? The boundary condition can be of any of these, either Dirichlet or Cauchy. And we say that what? It is Dirichlet if the boundary is given in this form. And then we talk about Cauchy if it involves t, which is time, at t equals to 0 with other conditions. Then we know that what we have is a Cauchy condition. And this at t is equal to 0 here is the initial time. So at the given function, let's say u of t or u of x, comma y, comma 0 is equal to 0, then of course we know that is the initial condition. So then we move on, then we talk about the method of separation of variable. This is perhaps the oldest and common method for solving partial differential equation, given the unknown function. And we say that what? If you are given a partial differential equation and you want to use the method of separation of variables, the first thing you need to identify is how many independent variables do you have. Once you identify the number of independent variables that you have, then the next thing, you are now going to assume a solution of the product or of the product of arbitrary functions of those independent variables. So here now look at it. This now has independent variable x1 to what? To xm. So we are going to assume a solution, the product of solution of x of x1, x of x2, x of x3 till xm of what? Of xm. So we then move on to this, and then I think we're able to give one or two theories here. And then before we now give our first example, we say solve this differential equation using the method of using the variable using the separation of variable method. And the first thing we did here was what? To identify the independent variables here, which are just what? X and Y. These are the independent variables. So for us to implement the method of separation of variable, then we are now going to assume two functions. Then the product of those two functions will be our assumed solution. So u of x, y, the first function is going to be x of y, the second one is going to be y of y, so they are product, and they must not be equal to 0. Then we now differentiate them with respect to x, with respect to y, then we substitute them back into this equation. And on doing that, we obtain this. Then we can now easily separate the two equations into those that depends on y and those that depends on x. That is why we have this equation 3. So we can see, by the time we look at this equation 4 here, we see that what we have on this side here only depends on x, while what we have on this side here only depends on what? On y. Then we can now say that, and this cannot be equal to 0. So we have to equate them to a constant so that we can solve them. And then we then equate these guys here to lambda. So on equating them to lambda, we're able to solve, then we resolve it into this and also into this. Then we now solve the two differential equations separately to obtain x of x and y of y. And this is what we have for our x of x, solving that, and this is what we have for our y of y. Then our u of x, y will now be what? The product of these two solutions, which is what we have in here. Same thing here, we say that we'll determine the solution to the 3D wave equation. Then we talk about solution of 3D Laplace's equation in curvilinear system. Here we provide the equations in two forms, both in cylindrical and the spherical. So we decided to look into the spherical form, and then we move on. Then we look at the spherical, and here we're able to identify the number of independent variables here. Here we have the r, we have the theta, and then we have the phi. So we're able to assume three functions, r of this, theta of this, and then this of this, and of course they must not be equal to 0. And then we differentiate them with respect to each and every one of the independent variables, then substituted back into this equation. So that actually gives rise to these given equations here. And then we succeeded in separating them. We separate the first one, then we have we separated it into two, which gives rise to these and this. And here now we solve these, and then we further separated these other equations. So we move on until we're able to obtain the given solution, which is equation this is what we have here. Then also we look at the three-dimensional wave equation. Also, we give this equation in both cylindrical and spherical, and then we solve the spherical form also, and then we move on by identifying the independent variables, then so that we can assume the proper solution for the problem. And then we're able to also look into this, and this is where we presented the solution to all the assumed function. Then we move on until we obtain the final solution, which we presented here for that wave equation. Then we now look at these again. We say obtain the solution of the transverse vibration of a thin membrane. Here we also have of course, here yesterday as we're doing it, we're able to provide. We say that of course this is the Laplacian of this u. Then we're able to open up to obtain the real equation, which is given as what we have in here. Then we also move on here, just since we are using just one method, which is the separation of variable method. And we said a lot about it yesterday because it is the oldest method of handling all these partial differential equations. So we're able to obtain all these differential equations, and then we solve them, and then we presented their solution. And then we move on to also provide us with the final solution to that given problem also. So we look into all these yesterday, and then today we have talked about the characteristics mapping method for solving the Euler equation. So we'll look at the linear advection, then we'll look at the general form of the transport equation, which is given in equation 2.1, and then we'll look at this is the graph of this file when t is equal to 0 to 2, and this one also, and this is when the velocity is constant, and this is when the velocity is what? is not constant. And then we saw the difference. And then we move on. Differential equation. We talked about these. These are inhomogeneous. This one is the initial condition. And then talk about these. And then we said, okay, what happened if the advector, the transport equation is homogeneous? Then we say that, of course, this f here will be equal to 0. So this part here for the solution will be what? Will be 0. So we are not going to have that part. And that is why we have it in this 2.7 as in the form as it is. So we move on that way. And then, of course, here we were able to show these representation of the characteristic curve. Yeah, for this, we'll show this. And then later, we also talk about remapping. Then we talked about the incompressible Euler equation, which we presented here. And then again, we then, after the presentation, then we were able to show that, the vorticity of these equations, Yeah, incompressible Euler. Then we look for the vorticity, which is the curl of what? Of U. And then the equation we obtained was what we have here in what? In 4.2. And we say that what happens if it is barotropic? That means what? The gradient of, that means the gradient of P cross P is equal to what? 0. So the equation will now simplify to what we have in equation 4.3. And then we then talk about what? The characteristics map. And then we say that this file here is the stream function and this one is the what? Velocity. So we are going to make use of these particular operation where we say that this one here is what we call the perpendicular gradient, which is giving us what we have in here. By the time we put these two together, is what we call Biot-Savart. For us to obtain U, we have to carry out the Biot-Savart. So this one is the Biot-Savart. So that, having said that, we look at this, and then here now we now talk about the algorithm for solving the characteristic mapping, the characteristic mapping method for solving the incompressible Euler equation, and then we're able to show the what? The algorithm. And this is where we stop with our lecture, and this is the end of our lecture.